squad. We're team number 5. My colleagues are John Paulos and Marcel Milanés, and myself, Juan Camilo Medina. And our project dealt with modular robots.
The outline for our project dealt with sensors, the 3D platform modeling, which is a design implementation, and the 4-legged gate development.
The main purpose of our project was to improve and develop a search and rescue modular robot. The reason why we choose a modular robot is because they can take any shape in the terrain. We focus in 3 areas in our project. One was actually to keep the modularity of our system. I mean, we didn't want to maintain 2 servers like stiff. We actually want to get all the movement from them. In addition to that, we wanted to integrate all the sensors in one platform to simplify our mechanism, and at the end also to improve on the weight of the actual system itself.
For the sensor enhancement part, we chose the QT110 touch sensor, which is less expensive than mechanical switches. It only uses a capacitor as an external part, and it operates between 2.5 and 5 volts. This is the schematic for the QT110 touch sensor. Here we ran an experiment using the touch sensor and the actual robot. After running a few simulations, we found out that it best works with humans and metal. Here for the infrared sensors, we chose 4 infrared sensors and placed them in a diamond shape, which gave us the best viewing angle of 120 degrees with a 30-degree overlap.
For the 3D platform, we focused pretty much on the power that it was going to be supplying the robot. So this is the casing that we choose for the batteries. The batteries are a little heavier than a 1.5 volt, and the reason why we choose that many holes is because it will allow us to reduce weight. In addition to that, we actually built a cooling system for the circuit board. As you can see right here, the battery fell. This is a SolidWorks 3D model, and this is the actual prototype built out of a 3D printing. Everything has been done at FIU. This is the lashing mechanism. We actually developed a lashing mechanism for future development, and pretty much what it's going to be doing is going to be attached to the modular robot, and a helicopter will deploy this system. And as you can see right here, this is all the mechanisms that will take part of our system. We have a camera. We actually implement 2 cameras. One is going to be for a long range, and one is going to be for a short range. Pretty much trying to simulate what a human being could do. And we're also planning to put a solar panel on the top to feed power to the batteries.
For the actual gate development, we employed inverse kinematic analysis for each one of the legs of the robot. And each leg can be represented as a planar 3R robotic arm, and those are the equations of the inverse kinematics. The first step to do the analysis is to select the trajectory that each one of the legs will be following, and I selected an arc first as a reference. I solved the kinematic equations for the arc, and then I realized that some of the joints were reaching singular positions. Why is that? It's because of the modularity of the robot. The servos are 180-degree servos, and it only allows a 90-degree relative angle between each one of the links. So keeping that in mind, I redesigned the path to be followed for each one of the legs, and this is the modified trajectory. And then to solve the kinematic equations again, well, I had an extra problem. Each one of the legs is a planar 3 degrees of freedom robotic arm. And so I had 3 variables and only 2 equations. So in order to make the system solvable, I needed to specify one of the joints positions all the time. So what I did is I did theta 2 equal to theta 3, and that simplified my equations, and I could solve them. So these are the results. This is for the rear leg. The kinematic analysis has 2 different solutions. They're also referred as closures, and the closure on the right violates the 90-degree constraint, and the closure on the left, it doesn't. It's actually good. These are the results for the front leg. Same thing, the closure on the right violates the 90-degree constraint, and the closure on the left doesn't. So the next step was to load the actual angle joints in a simulation to see what happened. First, I created a gate, and it wasn't very stable, so I improved it, and this is the result. So here you can see how the legs are moving. I wanted to use a conservative approach. I only wanted to move one leg at a time to maintain stability, and we knew that the servos weren't very powerful, so it would be moving slowly. And we were checking for stability all the time. So this is a side view of the walking gate. So you can see how each one of the legs recreates the motion in the simulation. And the idea is that all the joints are going to be moving forward, so all the legs are moving forward, although only one is up in the air, reaching the next position of the gate. It kind of like resembles an spider. I don't know, that's what it does to me. So we can conclude that the quadruped gate for the robot was successfully developed and implemented in simulation. And for the gate for future work, we observed that you cannot only model the floor as a flat surface. You can model the floor as an incline, as a slope, and you can also develop a turning maneuver.
To conclude the sensor enhancement part of the project, we adapted 4 IR sensors and a touch sensor to the new platform. And for future works, we would like to change the touch sensor for another one that could detect various materials.
And finally, for the platform modeling, we actually got to build it. And improvement for the future, definitely a stronger the material, but yet lighter. It could be PVC or plastic, but definitely we will go with this prototype. And we would like to thank Dr. Tosanoglu, Mr. Alejandro Lopez, Carlos Velez, that is in the audience again, and Adrian Art. And this concludes our presentation.
If you have any questions, we'll be glad to answer them. Thank you.
Thank you.